what we're going to have a look at now is one of the other factors that we, apart from length, that we talked about for affecting resistance. So we're actually going to have a little look at heat. So in order to do that, you would have been doing a practical with some light bulbs now, but obviously you can't, you're not here. Even if you've got light bulbs in your house, you haven't got any voltmeters and ammeters attached to them. So unfortunately, I'm going to have to do the practical for you on the desk instead. So I'm going to move the camera to point at the equipment that's here, and I'll talk you through what it is. And then it's very, very quick, and we will then sketch a graph instead of draw one properly. So let me just move the camera for you. Okay, so we've got the usual power pack, and the wires are plugging that into a bulb. And then what we would usually have in class is an ammeter and a voltmeter. But because you're at home and I don't want you sitting there writing down measurements of ammeters and voltmeters, which would be a bit boring for you, I've got, I know that's upside down for you, that's a current sensor. Which is going to measure the current for us on our behalf. And I've also got a voltage sensor, which is going to do the same for the potential difference. And then both of those things are attached to this box, which is called a data logger. If you might have used those before. And then the data logger is attached by a cable all to the computer. And then on the computer, I've got some software that's going to do its thing for us. So if I just share my screen, so there is a blank graph that hopefully the software is going to draw for us. So I'm going to leave the camera pointing at the bulb, which is going to look slightly boring, I think, until we get going. And what you need to be aware of is that if it's too small on your screen, you can toggle between the two feeds that I'm sending you at the moment. So you should have on your screen, if you're on a PC, if you pull up the People tab, you should see me at the top twice. If you're on your phone, if you turn your phone landscape, you should have the graph will be big on your screen, and then the camera will be a little thumbnail in the top right. But if you just either tap the thumbnail on your phone, or if you're on a PC, on the People tab, there'll be a tiny little like drawing pin symbol next to my name. You can pin whether you're looking at the feed from the camera or the graph that I'm sharing with you. So you can toggle between the two feeds yourself. You just choose what you want to look at between the graph and the bulb. I guess the graph will be slightly more useful to you than the bulb. Okay, so all I'm going to do, are we just, yeah, you're just watching Molly, don't worry about it. Just need to point out that I'm stepping a little bit to the side of the computer, which means that I can't quite see the chat as easily. So if I don't respond straight away, you might need to just unmute and say something. Okay, so the power pack is currently set on 0, well, thereabouts. There's the reading for the voltmeter and the ammeter. And all I'm going to do is start turning the PD up a little bit. And this is just what you did in class when you were measuring the resistance of those resistors at the beginning. So I'm just going to, we're on negatives, hang on. Just going to start turning that PD up. Now, this particular current sensor that I've got isn't very accurate for tiny, tiny, tiny little currents. So that first little wiggle about down by the 0, where it looks like it kinks a little bit. That's just that the sensor doesn't work very well. Also, I'm doing this practical really quick for your benefit so you don't get bored. So I'm not giving the sensors time to stabilize on a reading. I'm just blasting it through, which is why we're getting a bit of a cloud of dots rather than a line of dots. If you were taking your time over this, you'd turn the dial a little bit, and then you kind of count to 10 and wait for the readings to stabilize before plotting the point. But we're in a bit of a rush because I don't want you to get bored at home. So I'm just kind of gradually turning the dial at a kind of even pace. And I'm just clicking with the mouse just to tell it to plot the points over and over and over again, which is resulting in this kind of wide width to the line. But you could see that if we were going to draw a line of best fit, it would definitely go through the center of this big cloud of dots. If you've got the video feed on your screen somewhere as well, you can see that by this point the bulb is now glowing. And the fact that the bulb is glowing means that it's now hot. It must be at about 800 degrees in order to glow that kind of brightly as it is now, with a kind of whiteness to the color of it. So definitely we've got a hot piece of wire now. You'll remember that when you did the practical yourself in class recently, and you had this goal to try and keep the current down at about 0.1 of an amp. Well, we're well above 0.1 of an amp now, and that's resulting in the tiny little wire that's inside the glass of the bulb. That's making that wire get very hot indeed. And that's what we're looking at right now. We're going to try and ask ourselves what the effect of the bulb is, the bulb getting hot is. However, if you've paused to have a look at the axis labels on the graph that you're looking at, you'll notice that it's not actually a graph of resistance. I'm just directly plotting the potential difference on the x-axis across the bottom against the current on the y-axis going up the side. So this isn't actually a graph of resistance, and we're going to have to learn in a second how we manage to get the resistance from this graph. This graph is actually known as the IV characteristics. I'm going to stop it there. The IV characteristics of a bulb. Characteristics means what's it like, and IV means that, you know, we're using the current and the potential difference to try to get an idea for what it's like. And you can see that there's definitely a trend. Like I said, I was doing that really, really fast, and we've got a cloud of points, but you can see that we could definitely draw a line of best fit through the middle of that cloud all the way along it. And it would be a kind of curvy line. It starts off steep, and then it gets a little bit shallower as we go. So we're going to come back to what that means in a second. We're going to have to try and get a resistance out of that somehow. But then you'll notice that I've plotted the graph so that the origin is in the middle of the screen. And that's because what I'd also like to know is what happens if the current runs the other way through the bulb. Some components object when the current runs backwards through them. So we should just check whether or not the bulb cares about the current running backwards or not. So all I'm going to do to check that is that I'm going to swap over the positive and the negative on the power pack. So I'm just going to swap those wires over so that they're the other way around. And now we're just going to do the whole thing all over again and just see if it makes a difference. So while I'm doing that, you have a prediction in your head. Do you expect it to make a difference which way the electricity runs through a bulb? It's just a wire in the middle of the bulb that's getting hot. So if you do or do not expect it to make a difference, just predict in your head what shape you think the graph is going to be. I'll do this one a bit faster. We won't bother with such a big cloud of points. Okay, so is that what you were expecting? It's kind of symmetrical if you imagine spinning the graph paper around so that you were looking at it the other way up. It would look the same, wouldn't it? So that's kind of looking at the board again. What we've got here is a graph that's often referred to as vaguely S-shaped. So it's kind of starts off a little bit shallow here, gets a little bit steeper, then quite steep down through this middle section here, passes through the 0, and then it's symmetrical round the other way as if we had rotated the graph. So if you'd have been at school, we'd have had all the equipment out on your desk, and you would have done what you did before. You would have made a table with 3 columns in it, the potential difference, the current, and then another column for the resistance. And you would have drawn those 3 columns, and then you'd have plotted yourself a graph. So we're going to skip that bit, which is going to catapult us through kind of 3/4 of a lesson of practical work that I'm sorry you can't do at home. And we're going to jump straight to the conclusion bit. So you can probably toggle back to the camera now, and shall I just stop sharing and then it'll do it automatically. What I'm going to do is put a title and an introduction on the board, and you just need to find a place in your book where you can write this down. So, titles the IV characteristics of a bulb. Remember, I is for current and V is for potential difference. And the use of the word characteristics refers to the fact that we are trying to describe the behavior of the component. What's its character like? How does it behave? And we're going to be doing that in terms of the PD and the current, hence IV characteristics. Okay. What we were using there was the same testing circuit that we've been using in the past. So we've got the ammeter and the bulb, and then we've got a voltmeter attached either side of the bulb as well. That's our testing circuit. And then we've got the PD in volts and the current in amps. And we just kind of went 0, 1, 2, all the way up. And then we got these numbers for these. And that's going to result in a graph for us. And it's this graph that is referred to as the IV characteristic of the bulb. So we're going to do IV characteristics for a number of different components. The bulb is just the first one that we're having a look at now. And the only reason we've started with the bulb is because it's an example of a piece of wire getting hot. And we just done an experiment about a piece of wire of different lengths. And now we're doing a piece of wire of different temperatures. So this is the only tenuous link wire I picked to start with the bulb. Okay, so ordinarily, you'd have done this experiment, you'd have got real results, and this would be on a piece of graph paper, and it would all be plotted with a line of best fit. We're going to have to skip all of that, and we're just going to sketch it now. So sketch it means that you do in your book literally what I've just done on the board, which is just bung a pair of axes onto the page of your book. You don't need to label any numbers or any markings. We're not going to plot any points. We're just literally going to sketch what the graph looks like. And you remember from the screen it was a kind of stretched out S shape. So the thing that you just need to make sure you do is that you try to make it look symmetrical so that this bit is a little bit like this bit. Okay, so you try and draw yourself that vaguely S-shaped curve. And the reason I keep saying S-shaped in the hope that it'll fix in your mind is because a common mistake that students make, or not mistake, but in the moment they forget, students often remember that it's a curvy shape, but they muddle up which way it curves. So sometimes students draw it curving this way instead, which isn't an S-shaped curve. It's getting steeper and steeper and steeper instead of shallower and shallower and shallower. And that sometimes happens if you muddle up your axes and you get the PD and the current the wrong way around, or if you just forget. So I'm just going to keep saying S-shaped, 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 even though it's not very S-shaped, just in the hope that it helps you to remember which way around it goes. Okay, so the IV characteristics of a bulb. We've got the I and the V bit, but we haven't got the characteristics yet, have we? We've got a graph, but it hasn't described to us what's happened, or we haven't interpreted the graph yet. So what we need to do now is have a good look at it and ask, what's going on here with this bulb? What does it mean? What's happening? So what I'd like you to do is to have a little think about that while I just set this equipment up to do something slightly different. So you just look at this current and potential difference, and ask yourself, can you use that graph to deduce what was happening to the resistance of the bulb? So first question is, do you think that the resistance of the bulb remained constant, or did it change? If it remained constant, what is it about the graph that lets you say that? If it changed, why do you say that? What was it about this graph that made you think that? So is the resistance constant or not? And why do you think whatever it is you think? I'm just going to give you 2 minutes to think about that while I set the next thing up. Okay, what do people think? Just on the chat. Sorry, I'm just reading the chat. Marco, we've just done a quick experiment and now we're just copying down what's on the board. On the chat, could you please just write either the word constant or the word changes, and then we're all going to hit enter at the same time. So just don't press enter, but scribble out your word. Do you think that the resistance of the bulb is constant or changing? And I'm not going to pick on you, so don't worry about it. Just throw an answer out there and we'll see what people think. So if you could hit enter in 3 and 2 and 1 and now. Okay, so actually it's around about 50-50, isn't it? Maybe a slight nudge toward changes actually, but there's a lot of constants in there. Okay, it is changing. This graph is showing that the resistance is changing, but in order to understand why that is, we might need to just back off slightly and do the same experiment for something that we know is a constant resistance. So if I just shift the camera again, just briefly, I'll put it back in a sec because there's not really anything to look at. This is exactly the same experiment now, but I've just swapped the bulb out and instead I've put a resistor in its place. So you've already used these resistors and you've already done this experiment, but you didn't draw a graph for it, to have a look at the current and the current and the potential difference through a resistor. So if I just share the screen again. So again, remember, you can toggle between the graph and the camera if you need to. So we're just going to do exactly the same as we just did for the bulb. And this time, let's see what shape graph we get for a component who we know has a constant resistance because it's a fixed resistor. That's its whole job in life. So as we just draw this graph, so remember, it is going to jump around a little bit because I'm not really taking my time over it. So there's the fixed resistor. Now, if you were going to stick a line of best fit on that, I hope you'd agree that that's a pretty straight line. If you happen to have a ruler with you or just the edge of your book and you hold it up to the screen right now and you just put the edge of your book or a ruler across that line, you'll see that's a nice straight line. And likewise, I can just quickly swap over the positives and the negatives and push the current through the resistor in the other direction. And again, we get a similar result, just doing it quickly in the negative direction. So that's our graph for the fixed resistor. And so we can see that the IV characteristics of a resistance that doesn't change is a straight line, again, through the origin. What word were we using for straight lines through the origin? Do you remember? Stick it on the chat or just shout it out. Begins with a D and a P. Anyone? Yeah, well done, Rose. So for a fixed resistance that doesn't change, the IV characteristics is a directly proportional relationship, a straight line through the origin. Now, Why would that be? Well, remember, this is our equation. PD equals current times resistance. Well, if resistance is fixed and it doesn't change, then that's just some number. In fact, for the resistor that I've just done, the number is 10. It's a 10 ohm resistor. And our key bit for directly proportional relationships was that if you do something to one, the same thing happens to another. So we can just investigate that. So if the current was 1 amp, then 1 times 10 is 10. And now if we double the current to 2, then 2 times 10 is 20, which is the PD doubling. If we triple the current, then from 1 to 3 times the 10 gives us 30, and 10 times 3 is 30. So we do expect a direct proportionality if the resistance is constant, because it's just a scale factor to multiply it up. Whatever happens to the right-hand side of the equation will happen to the left-hand side of the equation. And what I'll do in a minute when we've finished with this is I'll just give you a quick note about the IV characteristics of a fixed resistor as well. But you can keep the straight line in your head for a minute. And so we could say, well, look at this graph here. And it does look like it begins life as a straight line. So if I just put that straight line on there, so that dashed line, that would be the line if the resistance had stayed constant. So down here, right at the beginning, when the potential difference was a tiny little number, like 0.1 of a volt, and the amps were a tiny little number, like 0.01 of an amp. When these numbers were really small, this line was quite straight. But then as the PD got higher and the current got higher, this line curved away. It stopped being this straight line. The resistance stopped being constant, and it started to change. So the question now is, did the resistance go up or did the resistance go down? So this is the line for the resistance staying the same. If it hasn't stayed the same, it's either gone down or it's gone up. Just give yourself 10 seconds to have a little think. Do you think that this line is showing the resistance going down or going up? Remember, neither of these axes are the resistance. We're not plotting the resistance on the graph, so you can't just read it off. You've got to deduce it, work it out. I'll give you 10, 20 seconds to have a think about that. Okay, so on the chat, just write up or down. And then we're all going to hit enter together. Oh, okay, you can start now. Max and Callum have gone down. Go on then, press your enters. Oh, there's a lot of downs. Oh, Toby's gone up, controversial. Okay, so let's think it through, because there's a lot of you gone down. Let's see if you're right. Let's imagine that the resistance didn't change for a second. So I don't know, let's pretend that right there is 4 volts. Actually, can you see the green very well? Shall I just stick to black? Okay, so let's set the power pack to 4 volts, and we'll just take this line up. Okay, if the resistance had stayed the same and hadn't changed, I would be getting this much current at 4 volts. But the resistance did change and the graph didn't stay straight. And so the dashed line isn't the proper graph. Actually, the graph is here. So that's what I would have got. That's what I actually got. I got less current than I would have done if the resistance had stayed the same. So I'm going to ask the question again. You can either stick with your answer, lots and lots and lots of downs, or you can change your answer to a different one based upon that argument. Am I trying to trick you or not? So start sticking your answers back on the chat again now. Do you think the resistance went up or down? Should we hit enter on 3, 2, 1? Toby's straight in there. Oh, now we're getting a mixture of up and downs. Some people have converted. Looking at something like what, 50-50 maybe? Maybe the ups have got it slow. No, maybe not. Okay, so resistance is all about reducing the amount of current that's flowing. Remember, the current is trying to fight its way down through a load of atoms, and the atoms are getting in the way and preventing the current from flowing. They're resisting the current. So resistors reduce current, and the bigger the resistance is, the more the current goes down. So we've just had the current go down. This is where it would have been if the resistance hadn't changed. But the resistance did change, and we ended up with less current. That means there must have been more resistance, because resistance is what makes the current go down. So in actual fact, when we were turning the dial up, and as the potential difference got higher and higher and higher, and the current got higher and higher and higher, we kept losing current. Down here, maybe at 2 volts, we lost a tiny little bit of current compared to what we thought we were going to get. Then maybe at 4 volts, we're losing quite a big chunk of current. And then if we take it up here maybe to 6 volts, then that's what we actually get, but we were expecting maybe that much. So the resistance is going up all the time. And worse than that, it's going up kind of at an increasing rate. So when we nudge it up a little bit at the start, we only lose a bit of current. We only nudge the resistance up a little bit. But the more and more we go on, the more this line curves away from the straight one, and the bigger the effect is, the more resistance we're getting all the time. So the conclusion is the current is never as high as it would have been if R had remained constant. R is, I've run out of board, but you can write it properly if you want. The resistance is increasing. Now, in terms of what to write in your book, you've got the sketch of the graph. I would put the little straight line on, the one I've dashed here, and I'd label it what would have happened if the resistance stayed constant. And then maybe do one of these dashy things to show that we're getting something lower than we thought we were going to. Now, some of you are going to do that faster than others. So if you finish making these notes here, what I want you to sit and think about is why. Why does the resistance of a bulb change when we crank up the PD and the current? What's going on? Explain it. I'm going to give you 1 minute. Another 30 seconds. Dylan, up or down? Brilliant. Okay, another 10 seconds. Okay, does anybody feel brave enough to unmute and suggest even the beginnings, even part of an explanation about why the bulb its resistance went up? Even if it's just a 2 or 3 words part of the explanation, because it's hard and we can build it up in bits. Anybody want to unmute?
Heat, maybe.
Say again.
Heat.
Heat, yes, definitely part of the problem. The bulb was definitely getting hot the more we cranked up the PD and the current. So that's actually the middle of the explanation, the heat bit. So you need to bookend it now. So why does the bulb get hot? And why does heat make the resistance go up? Any ideas? Kind of a chain of reasoning. Anybody want to fill in any other bits? Okay, I'll help you out again. Okay, so the very first thing I did to make this happen, which bit of the equipment did I touch to make this experiment happen? What was my hand touching? What was I changing? think if you were in class and you had the equipment, what was it that I was changing to do this experiment? Or another way of putting it was, what's the independent variable? Put it on the chat if you want to speak out loud. Okay, Molly's gone with current, which is one of our two variables, right? So 50-50, but unfortunately, the wrong 50. So we've got two variables, the PD and the current. On the power pack, get you a power pack. On the power pack, this dial on the front, that's the thing I was moving, that's the thing I was changing. I had control over that. That was the independent variable. That dial on the front is a potential difference dial. It alters the PD. So what I was doing at the beginning was increasing the PD. And remember, the potential difference is kind of the push. It's scooping up loads and loads and loads of electrons and forcing them down the wire. And as I turn the potential difference up more and more and more and more, it's scooping ever more electrons and shoving them down the wire. So as a chain of reasoning, what happens next? I increase the potential difference, and what's the consequence of that? The immediate consequence. Click on the chat if you want. Molly, you were nearly there last time. Missing a word. Current changes. Which way? Up or down? Up. Very good. Increasing the PD increases the current. So these two variables are related. We can see that as the PD goes up, the current goes up. And that would be kind of a really basic conclusion for this experiment if we weren't interested in the resistance, but we are. So PD goes up, makes the current go up, and I suppose I've missed an arrow out, haven't I? Shall we squeeze another arrow in there? Why does more current make the wire get hot? Now, this is the tricky bit. This is the crux of the matter. What's the current doing to the wire? I'll try sharing the simulation again, but it doesn't work very well through a video meet. It's a bit jerky, isn't it? It's not very clear even which way the electrons are flowing. But when I make more electrons travel faster down the wire, what will happen? Why will the wire get hot? Stuff an answer on the chat. It will heat up the wire, Callum, but why? Why will the current heat up the wire? Particles are vibrating, but why do they vibrate more? Yeah, the wires in the atoms are gaining more energy, Max, but why? What is the extra current doing? Why are the atoms vibrating more? Why are they gaining more energy? What's the electrons doing to them? I'm looking for a word beginning with C. C-O. L. Another L. Very good. Thank you, Rose. I'm going to stop sharing that again. Well, no, I need it. So just toggle back to my camera so you can see the board again. So increasing the potential difference makes the current go up. That means more, faster electrons. So there's more of them, they're traveling faster, they're smashing into the atoms much more often than they used to be. And this is making the atoms vibrate all over the place like crazy. And this is resulting in the wire getting hot, because remember, heat is nothing more than vibrating atoms. So when we say, that's hot, what we actually mean is, the particles in that thing I just touched are vibrating very quickly against my skin. So try saying that next time you burn yourself. So the wire gets hot. Brilliant. We've done the first half of the explanation. Well, more than half. You've managed to give me a chain of reasoning that starts with the PD going up and finishes with the wire getting hot. So now I have to ask, why does that make the resistance go up? Remember, resistance is how difficult the electrons are finding it to get through. Why are the electrons finding it harder to get through? Stick it on the chat if you don't want to speak out loud. Okay, let me show you that. I'll turn up the temperature and you tell me. So here it is, getting hotter and hotter and hotter. Molly, what's bumping into each other? So this is the hot wire now, the particles. Which particles? They're all particles. Particles in the wire. They're all in the wire. Do you mean the atoms or the electrons? The red ones or the white ones? Yeah, the red ones. So the red ones are now all out of place and the electrons are trying to get past. And can you see that it is way more difficult for the electrons to get past now when the atoms are everywhere compared to now when the atoms are all in beautiful, neat rows and aren't getting in the way? So the wire gets hot, and this makes even more collisions, higher resistance. I'm going to stop that sharing so you can all see the board, definitely. That's a really hard explanation. If you can get that down, if you can understand that, that's way up there, like grade 8, that kind of level. More PD means more current. More current means there are going to be more collisions. Those collisions are going to make the wire hot as the atoms vibrate out of position. And that's going to mean that there's going to be even more collisions between the electrons and the atoms, which means that the electrons won't be able to find their way through very easily. Okay. So I said that what I would do is give you a little note at the end about the IV characteristics of a fixed resistor, but we've run out of time. So I'm not going to do that now. We'll start next lesson with the IV characteristics of a fixed resistor, which we've already seen. And then we'll spend the rest of next lesson having a look at the IV characteristics of some other components as well. But for today, you've done really well. Lots of interaction on the chat. Some of you speaking up on your microphones as well. It's really good. Keep working hard, and I will see you next lesson.